just remembering the fact that atomic mass is really an average atomic mass, right? It is a weighted average between all of the isotopes of a particular atom. And we talked about that a little bit with chapter 1 and 2, right? About what an isotope is, which is, what's an isotope? Different neutrons, which makes different masses. Yep, okay? So atoms with the same element but have different masses, and so naturally occurring elements have all these isotopes, and the atomic mass that we report on the periodic table is a weighted average of those masses. And so we take this formula right down here, and we say that the percentage occurrence of some isotope A times its mass plus the percentage occurrence times some isotope B, and the percentage occurrence of some mass of isotope C. Okay, and we do a weighted average of all of those things. Okay, so again, I have an example down here on the bottom. We have an atomic mass for copper, or two isotopes for copper right here. Isotope A, isotope B, right? And we would say that as a percentage, 69.17% is 0.6917 times its atomic mass plus 0.3083 times 65. If we had to give an estimate as to where this weighted average would lean, which way is it going to be closer to? 63 or 65? Which isotope is more abundant? 63 is more abundant, right? It has almost 70% of copper atoms existing at a mass of 63. So our weighted average is going to be closer to 63 than to 65. So run the math on it and see what you get. Okay, we convert those percentages to decimals. Now let's just run the math. 0.6917 times 63. Okay, so I got a weighted average of somewhere around 63.62 AMU. Was that what you had? Somewhere? Or did you have different? Okay. That the average that gets reported on the periodic table for copper is like 63.5, I think. 63.55, so we're somewhere close to that, right? These numbers are probably made up, but that's how we calculate our average atomic mass. Remind me, what does AMU stand for? You're thinking harder than you need to. Atomic mass unit. That's it. Atomic mass unit, right? It's not even clever. Atomic mass unit. That's it. AMU. But what do we more commonly measure molar mass in? What's the unit for molar mass? Do you remember? Grams per mole. And so this is talking on the singular atomic level, and this is talking on the molar level, which we more commonly deal on the molar level anyway, right? In a bigger, more manageable quantities. We rarely look at a single atom, right? It's not really applicable for us. So, okay, very good. Comfortable there? All right, I don't think we need to do another example unless you guys think we do. We feel like we're good with how to plug it in? Okay, all right, good. Let's move on then. All right, molar mass is the mass of 1 mole of a pure substance. You can find molar mass of both elements and compounds. Molar mass of a given element is on the periodic table. So we just talked about the difference between these two. They represent the same numerical value. Okay, so they have the same number, but they have different units based on the scale at which you're examining your element, right? If we're looking at a single nitrogen atom, we would have an atomic mass of 14 AMU. If we're looking at a mole of hydrogen atoms, we would have a mass of 16 grams per 1 mole. Okay, so again, we're looking at the scale there. So much more common for us to use grams per mole, right? And to calculate molar mass. All right. So if I ask you to calculate molar mass, the periodic table is what we're going to have to really be reaching for, because our molar mass is given the same as the atomic mass. Determine the molar mass of a compound. We take into account molar mass of all of our atoms in that compound. We feel like pros at calculating molar mass. Simple, right? So how many hydrogen atoms do I have here? 2. How many sulfurs? Just 1. And how many oxygens? 4. So I'm going to take 1 times 2 plus sulfur. Do you know what it is off the top of your head? 32. You got your periodic table out, you little cheater. But you actually kind of know. Good. So you use them enough, you become familiar with them. And then we know what oxygen is. What is it? 16. Good. Times 4 of them. I don't know. I could probably do the math off the top of my head, but who knows? Really, who knows? Okay. So we get 98 grams per mole. 98 grams per mole there. Okay, because it asked us for molar mass, not atomic mass, that's why we chose the unit we did. Okay, what's the difference now down here? What do we run into with this secondary problem here? Yeah, good. That 3 has to be distributed through there. Okay, so I have 3 nitrogens. They weigh 14 each. So 14 times 3. How many hydrogens then do I have? 12. Not 7, but 12. So 1 times 12. 1 phosphorus, it has a mass of 31. Oops. And then plus 16 times 4. Okay, so we're looking at a little bigger number here. 14 times 3. Plus 12, plus 31, plus 64. I don't know, about 149 grams per mole. Do you kind of remember the guidelines I gave you for atomic masses on the periodic table? Or we can go whole numbers except if it doesn't, unless, we can go whole numbers unless it has something besides a 0.0 or a 0.9. Most of the elements we deal with, especially in that first 20, are 0.0 or 0.9. There's a few exceptions. But if we were going to use, for example, zirconium, number 40, I would want you to take that to 91.2. Okay, keep 1 decimal if we're not close enough to round to a whole number there. All right, easy peasy, okay? Moving into percent composition. Is that ringing bells? Percent composition is we're just finding out what is our compound made of, what is it composed of as a percentage of its mass. So we can find the percent composition of an element in a compound after finding its molar mass. Our steps are really just find the molar mass first, and then we can find out what is the part as a percentage of the whole, right? What is the part as a percentage of the whole? So if I want to find the percent composition of this compound, first thing I have to do is find the molar mass. Okay, so I'm going to come over here and do that. 24, right? 2 carbons, so 24 plus 5 plus 16 plus 1 gives me a molar mass of 46 grams per mole. And so to find the percent composition, I'm going to take carbon's individual part, which has a mass of what? Would it be 12? If I'm looking at carbon's individual part, it would be 24, right? Because there are 2 carbons per molecule here. So carbon's part of it is 12. And actually, I don't need to put grams there. 12 divided by the total gives me 26.1% carbon. Okay, we feel comfortable with that. You still have to multiply it by 100 to get it to a percentage, but I feel like that's a math step I can skip through. Okay, I got 0.2608. I went ahead and rounded that to keep 1/10 place there. So 26.1%. I would do 24. So sorry. I think I even said it out loud and then I just still wrote 12. So, okay, so sorry. Let's try that again. It's going to be double that. 24 divided by 46. How about 52.2%? Better? Yeah, thank you for correcting me. That'd be my carbon percentage. If I'm looking at hydrogen's percentage, how many hydrogens would I use? 6. So I'm going to take 6 divided by 46. And I get 13%. I got 13.04, so I'm going to keep that at 13.0 percent hydrogen. And then my last one was oxygen, and it has 1 oxygen of 16. So 16 divided by 46 gives me 34.8% oxygen. And so what should be true about these values? They should add up to 100, right? If I'm doing full percent composition, those three together should add up to 100. So 52.2 plus 13 plus 34.8. They should add up really close, and in this case, they added up to exactly 100. That's why I like to keep 1/10 place there if we need to, okay, just to check that. In all reality, if you're close, then that's fine. Okay. This says, what's the percent composition of calcium nitrate? Okay. Do you want to try that one, or do we feel pretty comfortable with calculating that? We feel good? Okay, fine with me. All right, let's move on then. All right, now we're going to get to gram and mole conversions. We're going to use our molar mass to help us convert between grams and moles. So if I want to go from grams to moles, or from moles to grams, molar mass is my conversion factor. Okay, so either one of these, I'm going to use molar mass. Okay, because the units for molar mass are grams per mole. Okay, let's try a couple here. How many moles are in 74.2 grams of MgCl2?
Did you skip a slide?
I don't know, did I? On yours? How many moles are in 74.2 grams of MgCl2? I'm always going to start with what I know. 74.2 grams MgCl2. We're going to go grams to moles here. What's moles always get? The what? The 1. Good. Okay, I couldn't tell what you were saying. And then with grams is always going to go molar mass. So I'm going to calculate molar mass of MgCl2. Okay, I got roughly that for my molar mass. I don't know if that's similar to what you had, hopefully. Chlorine, I keep it at 35.5. So with 2 of them, I know it's 71. And then my process is multiply across the whole top, divide by the whole bottom. So 74.2 divided by my molar mass gives me 0.779 moles of MgCl2. Okay, I chose to round there. Why? Do you remember? Why would I round that in that spot? 3 sig figs. That's the only reason. 3 sig figs. Okay. I wouldn't necessarily go off the molar mass sig figs because we can round that a lot of different ways. So I would go off of the sig figs you started from. Again, not going to be something I'm a real stickler about, but just something to keep in mind. When we're trying to make a determination on where to round, that's a good guide for you. Okay. All right, how many grams are in, I can't read what that says. How many grams are in 1.32 moles of magnesium nitrate? I shouldn't have said it. Would you have been able to name that? Hopefully. All right, moles is going to go on the bottom here. grams on top. Moles gets the 1. And our molar mass, let's see here. How many oxygens do we have? 6, good. That's what I had. I rounded it to 3 just because I started with 3 up here. Maybe I move them. Right? A molecule would be a compound. An atom might be just calcium or whatever it could be. That's the only difference. But they get used both with Avogadro's number. Okay, they both are used to look at the relationship between how many of those things are in 1 mole. Okay, because Avogadro's number works no matter what we're studying, no matter what compound, what element, it always, 1 mole of one thing is always that many, 6.022 times 10 to the 23rd. Okay, so if I have 1.4 moles of calcium nitrate, how many atoms are in that sample? This question actually is asking us something a little bit tougher than maybe what you think, because it says how many atoms are in that sample. So we're going to answer a bigger question first, and then we're going to take one more step. Okay? The first thing I want to do is find out how many molecules of calcium nitrate I have. Okay, so I'm just going to use simple Avogadro's number for that, 1.42 moles. 1 mole is equal to Avogadro's number worth. And so I'm going to take Avogadro's number times 1.42. And that tells me there are 8.55 times 10 to the 23rd molecules of this compound, calcium nitrate. So build calcium nitrate's formula for me and figure out what is calcium nitrate's formula. Calcium and nitrate. Okay, if I'm going to build that formula, I would end up with CaNO3 2. Okay, it's asking for how many total atoms are in that sample. Not how many molecules of my compound there are, but how many total atoms are in the sample. So let's break this down a little bit further. In this compound, how many calcium atoms are there? 1. How many nitrogen atoms are there? 2, right? And how many oxygen atoms are there? 6. So in total, per molecule, there are how many atoms? There are 9 total atoms per molecule. We agree? 6 oxygen, 2 nitrogen, and 1 calcium. So we know there are this many molecules of my compound. So to find out in total how many atoms there are, I would take that number times 9. And that would give me the total number of individual atoms. If it asked me for just the number of nitrogen atoms, I might just take this times 2, because I know that for every molecule there are 2 nitrogen atoms. But it's asking me in general how many atoms are present. And so I can take that times the number of atoms in the molecule. And I'm going to take that times 9. Okay, so that gives me about 7.7 times 10 to the 24th atoms. And it's not atoms of a particular thing because this is including all the calcium, all the nitrogen, all the oxygen. So we can't give it a label farther than that. Does that kind of make sense? Okay. Do you think you would have picked out the difference in that question? Or were you just going to stop here? Probably just going to stop there. That's easy to do. Okay, so then we just got to make sure that we're finding that distinction there. Okay. I'm around, but I did. Next one is simpler. So try this one on your own. If I have this many molecules of acetic acid, how many moles of acetic acid do I have? Do I really even need to know what acetic acid is? Not really, because do I need the molar mass? No. Nope. So I can solve this one without really even knowing what acetic acid is, although I'm sure you all know what it is off the top of your head, obviously. Agreed? Does our answer seem reasonable? Okay, we started with less than Avogadro's number worth of molecules, so it should make sense to us that we're coming out with less than 1 mole of our answer. Okay. All right, let's start putting them together here. If we have grams and molecules, what's the middleman between those two things? What's the middleman between grams and atoms or grams and molecules? What'd you say? Moles. The connector between them has to be moles. We don't know how many grams are in 1 molecule of something, and we don't know how many molecules are in 1 gram of something. Moles is our connector. Okay, so moles is our middleman. How many molecules are in 633.21 grams of barium permanganate? So I see grams and molecules, which means I will need to use both molar mass and Avogadro's number. Going to moles in between. Do I need to know what this formula is for barium permanganate? I will have to do that. So I'd probably do that first. Okay. You might need your periodic table out for that one. I'm not sure if I even know permanganate off the top of my head. MnO4. MnO4. Yeah, I wouldn't have known the charge though. Oh my, something went wrong there. Does it matter that we absolutely go across the top before we divide by something on the bottom? It doesn't really make a difference, right? I still had this number stored in my calculator, or so I went this divided by answer times that. right? It makes no difference the order in which we do that, right? I kind of preach about across the top, then around the bottom, but in all reality, it makes no difference, right? So my final answer came out about 1.01. Gosh, I started with 5 sig fig, so I guess I could take that farther. Times 10 to the 24th molecules. You don't have to necessarily, but I could, I guess, if I needed to. Expectations there, does it match what we were expecting? First and foremost, the fact that we were looking at molecules means we should be having a large number, times 10 to the 20 something. And secondly, we started with a molar mass greater than 1 mole of barium permanganate, so it makes sense that our number comes out larger than Avogadro's number. Okay. All right, try this one on your own. How many grams of oxygen? Just oxygen. How many grams of oxygen are in 6.244 times 10 to the 23rd molecules of potassium hydroxide? I want to see if we can problem solve our way through this one and see how we do. And if not, we'll break it down together. But I want to see how we work through this one. That's what I had. Did we have something similar to that? Maybe, yes, maybe. A couple different ways we could have gone about it. You could have found grams of your total compound and then done like percent composition if you wanted to do it that way. Is that what you did? Percent composition, that would have worked too. I just used my mole ratio here to take it one step further. And so I know that my ratio between individual oxygen and my total compound is 1 to 1, right? For every molecule, there was, I use the mole ratio between my individual oxygen and my total compound to say for every molecule of KOH, I know there is 1 mole of oxygen atoms. So that helped me with that mole ratio. If I would have used, let's say, a different formula, let's say that I did this, MgOH2, I would have had 2 moles of oxygen per molecule, and this would have been a 2 in my mole ratio. That would have changed it. I would have had twice as many moles of oxygen atoms per molecule, but that's not the case in this problem. I just want you to see how that could change. I can take the mole ratio to go in between individual atoms in my molecule as well. Okay, so actually all of those would have been 1 to 1 within our atom there, but I had about 16. Again, you could have gone this way. You could have gone through a percent composition pathway. Any of them would have been just fine. Okay, All right, this one is similar. How many atoms of oxygen are found in this many grams of lithium phosphate? So try this one on your own. Unless, do you want to work through this one together, or do you feel like you, based on that last example, can you work through this one on your own? You want to do it together?
I already did it.
Oh, you already did it. You did both. Oh, okay.
When you had it up on the screen, it said how many grams of oxygen, but this one that we had in our slides doesn't say oxygen, so I just went to this one.
Oh, my bad. Okay, so you already did this one first. Okay. Okay, well, we'll see what you get. Okay, all right, good. Okay, so if we're dealing with atoms, our T-chart is probably the way to go there and just look at the mole ratio. If we're dealing with mass, then percent composition could be a way to go. Just kind of depends on what your preference is. Do we feel comfortable with this mole ratio step right there? Bless you. We're switching from focusing on the full compound to now looking at an individual part of the compound. And so this step right here says that for every mole of lithium phosphate, there are 4 moles of oxygen. Okay, so we're examining that. Do we want to see what that looks like? Right, I've got a phosphate. I'm going to draw a real rudimentary drawing here. But we've got lithium, 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 right? I know that's not what it really looks like, but I just want to give you a visual, okay? And if I added another molecule of that, I would still have 4 atoms of oxygen. If I added another molecule, I would have 8 atoms of oxygen. But for every single molecule, I've got 4 oxygen atoms. Okay, so I just want you to see that relationship, that ratio. So we can put in a mole ratio step even when we're dealing with a component of the whole. All right, that's a little bit of a step up. Okay, that's where I'm going to stop us today for notes. We've got a CK12 that's on like moles and mole conversion, so pretty simple. We feel good about all of our mole conversions being able to move into stoichiometry next class. And balancing and reactions, all that kind of stuff is what we'll get to next class. Okay? So you've got a CK12. I saw it post at the beginning of class today, so you should have access to it on Google Classroom. It's not due technically until Tuesday, but I think you'll have plenty of time to get it done today in class. So we move plenty fast.